IB HLAA Vectors, day number 9. Topics for today are specifically applying what we now know about vectors in some scenarios that you might find in physics or other situations as well. There are many subjects actually that vectors are used for to calculate quantities. It is important to distinguish in this particular lesson between a vector quantity and a scalar quantity. So for example, displacement is a vector quantity since it has direction and magnitude, while distance is a scalar quantity and the magnitude of displacement. Velocity is a vector quantity since it has direction and magnitude as well, while speed is a scalar quantity, which is the magnitude of velocity. So you can see how distance works and coincides with displacement, as well as speed coincides with velocity. Now, acceleration is kind of tricky in some cases in that it is a vector quantity that has the same direction as velocity. However, we can also use acceleration as a scalar quantity in some contexts. So let's go ahead and get started. Okay, let's start with our first example here. Every year, Luca swims across the canal from Zadar to Preko. Let's draw a little something here. Here's Zadar, and over here is Preko. Okay, so let's use a dashed line segment to represent the path that he would desire to take, and read the rest of the question. His average speed in a pool is 1.8 meters per second, but there is also a current that is directly perpendicular to his route, and its speed is 1.2. Find the angle at which Luca must swim to travel directly to Preko. Give your answer to 3 sig figs. Okay, so let's say, for example, this current is traveling perpendicular to his desired direction of travel, 1.2 meters per second. Okay, so clearly what he would want to do here is to swim at this angle, right, in this direction, of which that vector right there would have a magnitude of 1.8 meters per second. Okay, so what we're trying to do in part A here is we're trying to determine this angle measure here. Now, we can clearly see that right triangle trigonometry would apply here, and it's very, very simple actually. However, you could also use some vector analysis, right, and find this angle here. We could call it phi, and use formulas that we know, right? We could take we could work with this vector, let's call it A, and this vector B, and we could find the angle between those two vectors, call it phi, by taking the inverse cosine of course, as we know, the dot product of those two. Now, you can tell that this is pretty labor intense and not necessary in this particular situation, right? The magnitude of both. So what I would do is kind of survey what you're trying to work on here, and take the simplest route. Now, of course, I wouldn't be done there. I'd have to take pi over 2 minus phi, and that would give me theta. Now, that's a lot of work considering the situation, how easy it can be. So let's pare it down to just that right triangle that we see and relate 1.2, 1.8, and theta. Well, the sine of theta will equal 1.2 over 1.8, as easy as this. Sometimes vectors make a simple situation more complex, so I would, in this case, take the inverse sine of this ratio, 1.2, 1.8, get myself an angle. Looks like I get 0.729 radians. And depending on the scenario and what they ask for, I would write this in both radians and degrees unless asked otherwise. Okay, so that angle there should be a 41.8 degree angle. Okay, part B says determine how long it will take if the route is 4.5 kilometers. Now, notice that our speeds are in meters per second, so I'm going to convert 4.5 kilometers to meters to keep things simple. Okay, so in order to do this step, we got to know our actual speed. Right, so we got to find that side length of that right triangle because the current seems to be working against us, so we would expect for that actual speed in the water to be less than 1.8. Okay, so what you could do is you could use Pythagorean theorem. 1.8 squared is equal to 1.2 squared plus, I'll call this s squared. If you calculate this out, s actually comes out to be about 1.34 meters per second. Okay, so there's our speed in the water headed toward Preco for Luca here during his swim. Notice that speed is equal to distance over time. Thus, time is equal to distance over speed. And therefore, the amount of time it would take for Luca to swim across the channel or canal, whatever this thing is, would be distance, which is 4,500 meters over 1.34 meters per second. This comes out to a pretty large number, long swim, 3,354 seconds, which is about 55 minutes and 54 seconds. All right, so in this case, just a lot of right triangle trig and some conversions. Let's look at another example. All right, example 2, Irma and Ida each have a drone that is flying at a constant speed. Irma's drone starts first and takes the path described in L1. After 3 seconds, Ida's drone starts and takes the path described by the equation L2. So we're going to refer to T as the time since Irma's drone has taken off, and S the time since Ida's drone has taken off. So particularly speaking, you can see that located here in each of these two vector equations for these lines. Okay, now I'm going to make a quick observation and say that I know that T is equal to S plus 3. Right, because of that 3-second difference between takeoff of Irma and then Ida's drones, I can rely on that. Likely, or very similarly, I could say that S is equal to T minus 3. Depending on which one is more useful, I will use that in a moment here. Okay, so part A asks us for the speed of each drone. So the speed of the drone is going to be the magnitude of the direction vector of each of those lines. So you can see the direction vector for Irma is going to be -2 plus 3, -2, 3, and 4. So I'm going to find the magnitude of that particular direction vector. Well, -2 squared is 4, 3 squared is 9, 4 squared is 16. So I would have square root of 29 meters per second. Okay, and I'm going to assume meters is the unit of travel here. Okay, so that's the speed of Irma's drone. Let's look at the speed of Ida's drone. So the magnitude of the direction vector for Ida's vector representation would be the square root of, looks like -2 squared, which is 4, plus 16, plus 49. So the speed of her vector, which is constant, both of these are constant, would be the square root of 69 meters per second. Okay, part B. Determine the distance between the drones just before Ida's drone starts flight. Okay, so what that tells me is I want the distance between the drones when t equals 3, which means that s is equal to 0, right before Ida's drone takes off. Okay, so what I would do is I'd find L1 at t equal to 3, and I'd find L2 at t equals 3, which implies that s equals 0. Okay, so if I were to take And for example, sketch this out. Let's go this point, we'll call it XYZ. For L1 would be equal to 2, -3, 0. That's the initial position of the drone for Irma, plus time t equals 3 times the direction vector, which is -2, 3, 4. Okay, so what that comes out to give me is this point. The point is the location of the drone after 3 seconds, which comes out to be, it looks like -4 and 6 and 12. Now let's talk real quick about the z component. The z component will be the height of the drone at that particular time. So z is always the vertical height. X and y are like distance. You could almost think of it as east-west for x, north-south for y, and then up and down for z. Okay, clearly L2, its location initially at time t equals 0 will be the following. And I'm gonna have, I'm just gonna name these vectors. Okay, I'll go -4 and 2 and 0. So clearly you can see that both of these drones start on the ground. Okay, so I'm gonna call this point point A. That's the location of Irma's drone at time 3, and point B, the location of Ida's drone at time t equals 3 or s equals 0. Now, what we need to do is we need to find the magnitude of the vector connecting those. So first I'm going to find A to B. I'm going to find that direction vector. And A to B comes out to be, looks like 0 and -4 and -12, right? So that's the change in the x, y, and z to get from A to B. So the magnitude would be the square root of 0 squared, which is 0, plus 4 squared, which is 16, plus 144. So it looks like the distance between the two would come out to be the square root of 160, which can be written as 4 square roots of 10, which is rounded off to 12.6 meters. So that's the distance between the two drones the moment before Ida's drone takes off. Okay, part C. I'm going to work part C on the left side here. Part C says that the drones will collide, which means that they will both be at the same location at the same time. Since I know that t is equal to s plus 3, what I'm going to do is I'm going to take the z component for each. Okay, the z component for Irma's drone is going to be 0 plus 4t, and the z component for Ida is 0 plus 7t. Excuse me, 0 plus 7s. Now I'm going to do a quick substitution. It asks me to find the time or how long Irma's drone has been flying when this has happened. So I want to find t. Therefore, what I'm going to do is I'm actually going to use this form where s is equal to t minus 3. And I'm going to plug that in for s below. Okay, so I'll get 4t is equal to 7 times the quantity t minus 3. All right, and I'm just going to solve. Okay, so what I get is 4t, I'm going to solve for t, 7t minus 21. Therefore, 21 is equal to 7t minus 4t, which is 3t, and thus t equals 7. So the collision happens when Irma's drone has been in the air for 7 seconds. Okay, so part D, I'll do that over here to the right side. It says find the altitude of the collision site. Okay, we talked about altitude. Altitude is the z component. So what I'm going to do is I'm going to take t equals 7, and I'm going to plug it into the z component for Irma. Now, it shouldn't matter which component I plug it into. If I plug it into Ida's component for z, I got to make sure I'm plugging in the appropriate value for s. S would equal 4. So either should work. I'm going to plug this into the z component, which of course was 4t. If I plugged s into the z component for Ida's drone, I would plug in for 7s. And if I plug those in, you should see that you get the same number. All right, so the vertical height or the altitude would be regardless of which component and which vector you work with, ends up being 28 meters. All right, there you have it. Irma and Ida, sorry, you gotta go buy new drones at Costco. That's a shameless plug, I guess, for Costco. All right, let's do one more example. Okay, last example for this set of notes. Hannah is skiing on a slope at a 35-degree angle to the horizontal. Okay, so let's attempt to sketch this. Here's my slope for Hannah. 35 degrees to the horizontal means that this angle right here is 35. Okay, so let's note that. Okay, so just for the purposes of my diagram here is Hannah, and she's about to head downhill. I'm going to label a few vectors here along the way. Okay, we're going to make a few vectors here, and I'll explain them in a moment. Okay, so I've got R, I've got N. N has the same magnitude as R. I've got W. Where's W going to be? Here we go. Let's go like this. Okay, I've got this vector P, which is equivalent to this vector P here. And I'll go with one more color. I gotta find a different color. Let's go purple. That'll work. We'll go T. Okay, so let's get down to it. Hannah is skiing on the slope at a 35-degree angle to the horizontal. Given that she has a mass of 30 kilograms, find the following. What is Hannah's weight? Okay, so Hannah's weight is going to be represented by the yellow vector W. All right, so her weight due to acceleration and her mass. So let's talk about that for a moment. Force, in this case, is equal to mass times acceleration due to gravity. Okay, so acceleration due to gravity, we're going to consider 9.81 meters per second squared. Her mass, in this case, is 30 kilograms. And the force will be given in newtons. So force in this case, for part A, will equal mass times acceleration. So 30 times 9.81. Okay, so force will be equal to 294.3 newtons. That will be equivalent to the magnitude of W. Okay, part B. Part B, the magnitude of the reaction of the slope on her weight. That is going to be the magnitude of vector N, which is equivalent to the magnitude of vector R. Now we got to find a way to find that value. Okay, so let's analyze this triangle here. This is a right triangle, and this angle right here is going to be congruent to the angle to the horizontal at which we're skiing, right? We could use some geometry to get there. You can do that on the side, but that'll also be equal to 35 degrees. Therefore, if I want to equate the vector N's magnitude to the vector W's magnitude, I could use a cosine function. So the cosine of 35 will be equal to the magnitude of N over the magnitude of W. Well, I know the magnitude of W, and I know the cosine of 35. Therefore, the magnitude of vector N would be equal to the magnitude of W given above, which was 294.3 newtons, times the cosine of 35. So the magnitude of vector n, which is equivalent to the magnitude of vector r, is going to go ahead and be equal to 241 newtons. Okay, let's look at part C. Hannah's speed from resting to 50 meters down the slope, given the traction vector has a magnitude of 80 newtons. So we want to know Hannah's speed as an end result. In order to know Hannah's speed 50 meters down the slope, what we got to do is we got to work a little bit with the green vector P and the purple vector T. So we're given some information here that the purple vector, which is the traction vector, right, has a magnitude of 80 newtons. Okay, so the traction vector is working against her skis. This vector P is working with her skis, right? The force of gravity. What we need to define is a new vector, and let's call it D. Okay, and D will look kind of like, I should probably use a different color, but we'll go with that. D is going to be a vector representing how much force will be applied in the direction of the slope. So the magnitude of vector D is going to be equal to the magnitude of vector P minus the magnitude of vector T. Okay, I'm not going to use colors. It's just going to take too long. Okay. So P is the force of gravity on that slope. T is the traction vector, which is the force of the traction at which the snow provides some kind of resistance. And therefore this direction vector down the hill would be P minus T. Okay, so let's find P real quick. I'm going to do a little bit of the side work over here. Okay, so we can look at this triangle that we have below here again. We know this angle is 35. We know we're looking for the magnitude of P, and we know the magnitude of W. Therefore, I could say that the magnitude of P over the magnitude of W is equal to the sine of 35. And therefore, the magnitude of P is equal to the magnitude of W times the sine of 35. All right, based on my calculations, the magnitude of W times the sine of 35 comes out to be 169 newtons. Okay, we know the traction vector. The traction vector has a magnitude of 80. And so now we can find this direction vector downhill, which would be the magnitude of P, 169, minus the magnitude of T, which is 80, giving us 89 newtons. Okay, so let me outline part C here. Okay, so we know that force equals mass times acceleration. Well, the acceleration due to gravity is going to be slowed slightly based on going down the hill as opposed to just falling out of the sky. So the magnitude of D is equal to mass times the magnitude of acceleration in the direction of the hill. So if the force downhill, which we know is 89 newtons, is equal to mass times acceleration, or the absolute value of acceleration, what we get is that the absolute value of acceleration is equal to 89 newtons over the mass. And in this case, the mass is 30 kilograms. Okay, so now what we know is we have the acceleration due to gravity on this hill. Right, so the acceleration due to gravity would be 2.96 meters per second. Okay, review that real quick. Force equals mass times acceleration. We know mass. We know the force on this hill, downhill, considering all variables, right? Considering the traction vector and the direction vector P, we now know D, which is the pure version of the force headed down this hill. Okay, so we know the magnitude of the acceleration on this hill based on all the variables. Okay, so what we need to know is Hannah's speed. Now I'm going to use this property right here. The magnitude of the velocity squared is equal to 2 times the magnitude of the acceleration times what I said earlier, which was that, well, maybe I didn't say this earlier, but s is going to be the change in distance. Okay, so let's go ahead and finish off part C here. Okay, so if the magnitude of velocity squared is equal to 2 times the magnitude of the acceleration times the change in distance, then what that tells us is that the magnitude of velocity, which is what we're looking for, would be the square root of 2 times the acceleration times the change in distance. So we know 2 times the acceleration will be 2 times 2.96 times the change in distance. Well, we go where she goes 50 meters down the hill from resting. Therefore, velocity in this particular situation, if I took the square root of that expression, I would get 17.2 meters per second. Now this right now at this point, I haven't derived this, so this is just something you should know. Force equals mass times acceleration. If you're not in physics, you should memorize that as well. Okay, part D. Part D says the maximum angle of the slope so that Hannah will not slide at all. So what we want is we want for P to equal T. We want the magnitude of P. Okay, let's highlight that. The magnitude of P to be equal to the magnitude of T. Right? If that's true, if the traction vector is equal, is equal to the direction vector, then she's not going to move at all. Okay, so the magnitude of P. What is the magnitude of P? That's the magnitude of W times the sine of theta. We talked about that above. Okay, so if that's true, and I know the magnitude of T, the magnitude of T is 80. Okay, so if I want W sine theta to be equal to 80, then that means theta will be equal to the inverse sine of 80 over the magnitude of W. And the magnitude of W is 293. Oops, no, 294.3. Okay, so if I take that and I work that out in my calculator, it looks like at an angle of 15.8 degrees, Hannah's not going anywhere. All right, guys, that's applications of vectors. We'll see you next time.